None of you guys had physics last year, did you? So.
Are vectors harder than what we just learned? No.
I know they're different.
Okay.
They're different. Okay. This chapter 6 goes a totally different direction with vectors. Okay, so total different direction. So I'm not gonna say it's easy, but I don't think it's more difficult than what we've just done either. So okay, a vector. Okay, so we're talking a physics term here. By definition, is a directed line segment in the coordinate plane. Okay, so directed line segment because a vector has direction with it. Okay, so line segment, basically it looks like a ray. Okay, written as PQ, where P is what we would call the tail of the vector, and Q is what we would call the head of the vector. Okay, and that would be the case where P, the tail of the vector, is the ordered pair x1, y1, and it's also, besides the tail of the vector, it's also the initial point. Q, up at the head of the vector, is the terminal point, and it's x2, y2. So you have your first set of ordered pairs at the initial point, your second set of ordered pairs at the terminal point. Okay? Now, given your initial and terminal points of your vector, so given those two ordered pairs, you can find the component form. Component form is something we're going to do a lot with. Okay, the component form of the vector is basically, it's written as an ordered pair, except instead of your typical parentheses, I don't know what they're called, but they're like pointy parentheses, triangular parentheses. There's probably a name, but I don't know it off the top of my head. Okay, so where your vector and component form is written as V1, V2, where V1 is found by subtracting your x's, always x2 minus x1, and V2 is found by subtracting your y's, always y2 minus y1. And so what I'm saying here is it's always the terminal minus the initial points. Or the, easier way to remember it, the head minus tail rule. Okay, so if we're looking at the head minus tail rule, we're looking at where the arrow is minus the initial piece. Okay, so HMT, if you see me write that, or head minus tail rule, can also be used to find component form. So whichever way you want to remember this. And then the component form of the vector is also sometimes called the position vector. Okay, so trying to give you a little bit of vocabulary, so depending on what you're asked, you can hopefully answer the question. Another bit we're going to talk about is the magnitude or length of the vector. So length, you guys obviously understand the word length. If you're asked about the magnitude of the vector, the magnitude is another word for length. Okay, so the magnitude of the vector is determined by finding the distance between the initial and terminal points. And so I don't know if this formula right here, the second one, looks familiar to you. The square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. You've done this formula before. This is the distance formula. It's the distance one. We always learn them together, right? Yeah, the distance formula, so the distance between two ordered pairs, okay, is this right here. Well, if you're trying to find the length of a vector, you're trying to find the distance between the initial and terminal points. Okay, so you see it if you have the two ordered pairs, you can do it like this. If you just have a vector, and I'll show you, if you just have a vector in component form, you can just look at v1 squared plus v2 squared and do that square root. Okay, so this is magnitude or length. What symbols does that look like is around the v for that magnitude?
Absolute.
It looks like absolute value, doesn't it? Okay, so the magnitude or length can also be called the absolute value of v, because it is just that. Okay, so again, a little bit of information. I'm kind of giving you all the information, and we'll go into examples. And then we're going to just do some basic math with vectors today. One of the things we're going to do is we're going to add two vectors. When you're adding two vectors, you just simply add I use the word like, but you add the components. Okay, so when you're adding two vectors, you add what I would call the like components. So you add the x with the x, and you add the y with the y. Okay, so that's adding components for two vectors. And then when you're multiplying, so we'll say multiplying a vector by a vector for another day. That's another lesson. Okay? But when you're multiplying a vector by a scalar, or in other words, just a constant, a single number, then basically it's like a distributive property. You take that scalar or constant and multiply it by each component of the vector. Okay? So, a whole bunch of basic information there. Let's work on what some of these questions ask and how we should apply this information. So example 1. Directions ask me to find the component form and magnitude of the vector v equals vector pq, where p is defined to be negative 3, 4, and q is defined to be negative 5, 2. Okay, let's start with component form. If you look back up above, any thoughts on how we can find component form?
Negative 30 minus negative 5 for V1.
Almost. So you subtract your x's. The catch is, if this is vector PQ, what does that mean? That means if it's vector PQ, P is the initial point and Q is the terminal point. So it's the point at the head of the vector. Okay? And if you look at how these points are defined then, if that's the case, since P is the initial point, we're going to call that what? That's x1, y1. And that makes Q x2, y2. Well, it is specific when you find component form there that in order to find your V1, you're going to do x2 minus x1. Okay, so yes, I'm being nitpicky, but we have to switch it around. We can also think heads minus tails. Okay, so the HMT that I wrote up there, okay, my brain tends to go to just heads minus tails, okay, the head of the vector being where the arrow is. And so that's going to be our Q there. So with that in mind, I'm going to say V equals, so for the x's, heads minus tails, negative 5 minus negative 3 is going to find me V1. And in order to find me V2, we're going to repeat the process with the y's. And so then we're going to be, again, looking at heads minus tails. Thank you. And we're subtracting what? 2 minus 4, right? Heads minus tails, so it's Q minus P in this case. Clean it up and you have your component form. Negative 5 minus negative 3 is?
Negative 2.
I prefer negative 2. Negative 5 plus becomes negative 5 plus positive 3. And then 2 minus 4 is?
Negative 2.
Negative 2. Okay, right there, you have found your component form.
Pardon the interruption. Autumn Buster, you need to report to the high school office. Autumn Buster, report to the high school office.
And with our component form, okay, this is our vector V. Our component form is, in each piece of this, is V1 and V2, if you want to label those. Okay, so if you have basically the endpoints of the vector, the head and the tail, it's a subtraction. Okay, you have to get the order correct though. That's the catch there. Now, the other thing we were asked to find was the magnitude. You just use all your space. Okay, how do we find magnitude?
Absolute value of V.
Okay, so magnitude is absolute value of V. And we have a formula there, don't we? That formula, and there's two different ones written. And we can do the square root of v1 squared plus v2 squared. I'm actually going to start with the other one just to prove a point on my behalf. But you can definitely just go straight to the square root of v1 squared plus v2 squared. Because did we just find v1 and v2? We did. Now, if you didn't have v1 and v2, what would you have to go back to? The x's and the y's, right? And if we do x2 minus x1, that's negative 5 minus negative 3, quantity squared, plus y2 minus y1, 2 minus 4, quantity squared. Do those pieces that I just fill in look familiar? What I just filled in those parentheses, isn't that what we just used to find v1 and v2? It is, okay? So thus, I'm just trying to show you the connection there. So if you went ahead and said v1 squared plus v2 squared, you're just a step ahead of me, and that's great. Negative 5 minus negative 3, we already said was negative 2 squared, and 2 minus 4 is negative 2 squared. So if we square those, negative 2 squared is 4. Negative 2 squared again is 4. What do we know about 4 plus 4?
8.
It's 8. Okay. And what do you know about the square root of 8?
Is it can be rationalized to 2 square root of 4 of 8?
Okay.
Oh, yeah, right. Yeah. 2 square root.
So we know 8 is 4 times 2. 4 is a perfect square. The square root of 4 goes out front as 2, and that leaves a 2 underneath. So the magnitude of the vector is 2 square root of 2. Or in other words, the length of the vector is 2 square root of 2 units. Okay? So that's one or two topics you'll be looking at in homework. Component form and magnitude. It's basically a plug and chug. Okay? Okay. Ready for example 2? Okay. Example 2. U. And if you haven't noticed, U and V are common letters they use for vectors. Does it have to be U and V? No, but that's what you most commonly see. So we have U defined to be the vector negative 1, 3. Okay. And we have V defined to be the vector 4, 7. And it's asking us to find the component forms of the following vectors. And so A asks us to do U plus V. Well, what is U?
Negative 1, 3.
Negative 1, 3. Plus, what is V? 4, 7. So if I fill in what U and V are, this is what it shows. We're doing the vector negative 1, 3 plus the vector 4, 7. How did it say we're going to add vectors up above? Add the components. Which adding the components means you're adding V1 with V1. Or I guess it would be U1 and V1. And you're adding U2 and V2. So this means I'm going to be adding, for the first position, negative 1 plus 4. And in the second position, I'm going to be adding 3 plus 7.
Why are the parentheses
Why are the parentheses what?
greater than less than?
Because that's what you use for vectors.
Just because that's it.
I don't know, there might be different reasons out there, but that is vector notation. So, I personally don't have a better answer than that. You know, I'm a math major, not a science major, so my physics is a little weak here, but
Our vectors. Mine just keep looking like 7s and confusing me.
you do have to be very careful. I totally understand because mine tend to get
A little wonky.
a little wonky, and then what is that, you know? So, but yeah. So vectors are physics. Okay. If you, I guess there's only 2 of you, they'll be here next year, but if you take physics next year, you would learn about vectors. So, okay. So that was adding 2 vectors. B asks us to do 3u. So what's that saying we're going to do?
Distribute.
Yeah. You're going to do 3 times the vector, -1, 3. If you look up above where it said when multiplying by a scalar or constant, okay, scalar is another word for a constant, we simply distribute. So this is going to be, you're going to be doing 3 times -1 and 3 times 3. What do we get? The vector -3, 9. So if the end to that looks like 97, what's it look like at the beginning? Backwards 7?
Maybe. My beginning ones normally look fine, and then the end ones.
It's the end ones that, yeah. And I don't feel like I can draw the sign the same 2 times in a row ever.
No.
I feel like they look different every time, so. Okay. C. 2u plus -1v. What do you think we're going to do?
Multiply and then add.
Multiply and then add. So 2u means I'm going to take the vector u. I'm going to multiply each piece by 2. So I'm going to do 2 times -1 and 2 times 3. Plus -1v means I'm going to take my vector v and multiply each piece by -1. So -1 times 4 and -1 times 7. Okay, so 2u becomes the vector -2, 6. -1v becomes the vector -4, -7. And then you are adding your pieces. What do you get when you add?
-6, -1.
Okay. -2 plus -4 is -6. And 6 plus -7 is -1. So I have the vector -6, -1. Okay. When you're ready, obviously flip over to the next page. We've got a piece of vocabulary here, which talks about what an unit vector is. Okay? A unit vector is a vector with a magnitude or length of 1. Okay? Because when we talk about a unit is a length of 1. So a unit vector is a vector that has a length of 1. Thus, given vector v that is not the 0 vector, the following formula is used to find the unit vector. So in other words, this applies to find the unit vector with the exception of 0, 0. It doesn't work for 0, 0. So in order to find a unit vector, the formula is written in 2 forms here. Okay? I tend to personally use this first one, where the unit vector is equal to 1 over the absolute value of v times v. However, realize this second form, u equaling v over absolute value of v, that is just the 2 pieces multiplied together, right? So they're the same thing. You do you. You can use whatever form you want once you figure out what we're doing. When you're setting this up to find u, absolute value of v, what are we going to put in for absolute value of v? That's going to be the, what's the word for absolute value of v? Magnitude. Okay, so that's going to go in the bottom of the fraction. And then realize that v off to the right, that's just the vector in component form. Okay, so this v right here just represents component form. Okay, so example 3. Example 3 asks us to find what? Well, a unit vector, of course, because I just gave you a formula for a unit vector. Find the unit vector in the direction of v equaling -3, 2, and then verify it has length 1. Set that aside in your brain for a moment. We'll talk about that later. Let's start by how do we find a unit vector in the direction of v equals -3, 2. In order to do the unit vector, we're going to use the formula I just circled, right? What do I have to know? We have to know the magnitude. Do I know the magnitude? Not yet is the key. Okay, so let's start by finding the magnitude. In order to find the magnitude, what are we doing? Flip to the front side if you need to. Okay, magnitude is the one that is the absolute value signs. Absolute value of v. What are we doing?
Is v1 plus v2, or v1 squared plus v2 squared?
Okay, so it's the square root of v1 squared plus v2 squared. What's v1?
-3.
-3. And what's v2? 2. So it's going to be the square root of -3 squared plus 2 squared. Well, -3 squared is 9. 2 squared is 4. 9 plus 4 is 13. So what is the magnitude? Square root of 13. Okay. Now, magnitude is not what we were really asked to find. We were really asked to find the unit vector. So, before we could find the unit vector, we had to make sure we knew the magnitude. What else do we have to know? We have to know v, or in other words, the component form. Do I know that? Yeah, that's what this is. This is component form. So we're ready to go with finding our unit vector. So I'm going to write out my formula so you know what I'm plugging into. U equals, and I'm going to use the first one, 1 over the absolute value of v times v. So fill in your formula. 1 over, what was the absolute value of v? Square root of 13 times v. V, as I said, is just a vector in component form. That was given. What is our vector in component form? -3, 2. Now, I would go one more step. 1 over square root of 13 hanging around out front.
Rationalize it?
No, I'm not going to make you rationalize. But 1 over square root of 13 hanging around out front of that vector is, it's like a constant hanging out there. What can you do with a constant? Distribute it, multiply it in, yes. So we're going to take that 1 over square root of 13 and we're going to multiply it to each piece. Okay. Just think fractions, folks. 1 over square root of 13 is a fraction, yes? What's -3 as a fraction? -3 over 1. How do we multiply fractions? Straight across. Top times top, bottom times bottom. So the first one, 1 times -3 is -3. Square root of 13 times 1 is square root of 13. So the first component is -3 square root of 13. Second component,
2 over square root.
okay, 1 times 2 goes on top. Square root of 13 times 1 goes on bottom, which is square root of 13. And you have your unit vector.
Yeah.
Okay? We are done with that part of the problem.
Minutes.
Oh, you're talking about are we done with notes today?
I wasn't.
Okay.
I know.
My seniors are over it. Maybe my juniors too, but definitely my seniors. Okay. We still have to finish this problem. I mean, I'm not stopping mid-problem here.
Oh wait. What? Oh, verify it has a link.
Okay. Find a unit vector. Okay, check that off. And verify that it has length 1. How am I going to verify it has length 1?
Well, I'll probably
Find the length of it.
No, you're so smart.
Do we have a formula to find the length of it?
Yeah. Isn't it the same as the magnitude?
Right, exactly. Length and magnitude. Same thing in vector world. So when we talk about finding the length, we're finding it's our absolute value formula. So we're finding the absolute value of our unit length. Okay, so this is going to be our verify. What do you remember about that formula?
V1 squared plus V2.
Okay. V1 squared plus V2 squared, the two components of the vector, right? In this case, the first component is -3 over square root of 13. We're going to square that. Plus the second component squared. So 2 over the square root of 13 squared. All under the square root. Now, the math is good here, folks. Okay. We have to square each of these. -3 over the square root of 13 squared. Well, what is -3 squared? 9. What is the square root of 13 squared?
13.
13. So this first fraction is 9/13 plus, now it's 2 over the square root of 13 squared. What is 2 squared?
Oh,
What is square root of 13 squared?
13.
13. So now I have 9/13 plus 4/13. What's 9/13 plus 4/13?
13.
And what do we know about 13/13?
Equals 1.
It equals 1. And what do we know about the square root of 1?
Equals 1.
It is 1. What did we just do?
Verify.
We verified that the length is 1.
That was quite great.
Okay?
Alright. Good job.
So there's kind of our proof that it does work. Okay? That is proof that it does work. Okay. Continuing along. As we look at, okay, so we've talked about this component form here, right? Where we have the V1 and the V2. That is your most common way to write a vector, is with component form. However, we're also going to talk about a slightly different way to write it, which is using our unit vectors and doing a linear combination. So, there are two basic unit vectors. I is the one that is the x component. So I is defined to be the vector 1, 0. And j is defined to be the vector 0, 1. If you think about that, that's just your 1 over and your 1 up. All vectors can be written based on these two unit vectors. So the idea here that if you have a vector a, b, okay, this is kind of our proof here. If you have a vector a, b, do you agree it could be split into a, 0 plus b, 0? Like if you think backwards, if we added a, 0 and 0, b, that would add up to be a, b, would. Okay, so we can take one vector and split it into two. Okay, we can also essentially factor out those components, the a and the b. So if you factor out the a divided by a leaves me with a 1 in that spot. If you factor out a b divided by b leaves me with 1 in the second spot. Okay? So the idea that the vector a comma b can be written as a times 1, 0 plus b times 0, 1 leads us to the fact that a vector in linear combination is a times vector, the unit vector I, plus b times the unit vector j. Okay? Now, this is what we refer to as a linear combination. Okay? And again, remember, I and j are defined up there. Okay. Easy example to make this make sense. We just had this unit vector here. Okay, this was in our normal component form. Could we take this vector here and write it as a linear combination? Yeah. Okay. If it's a times I plus b times j, what is your a value? Your a is your negative 3 over the square root of 13. And what is your b? That's your 2 over square root of 13, yes? So, for example, and I'm just going to bring it over here, if we write that out as a times I, well, a was negative 3 over square root of 13, and then that would be times I, because it's in the first position, plus b is the second position, so 2 over square root of 13 times j. That's what your linear combination looks like. Okay, it's just saying that we can take a typical component form and rewrite it as a linear combination. Okay. Well, we're going to use it in other ways down here. I'm just trying to show you the connection that how does the vector a comma b become the linear combination a times I plus b times j. Okay? Now, okay. By using this format, we have a linear-like combination using the vectors I and j. These scalars or constants, a and b, are considered the horizontal and vertical components of the vectors v, respectively. So a is your horizontal component. B is your vertical component. It's just essentially like the idea of x and y. Okay? The direction angle of a vector v is the angle theta that the vector makes with the positive side of the x-axis. Using trigonometry, this is how we still relate to what we've been talking about, okay? Using trigonometry, the horizontal component of a vector is, so A is the absolute value of v times cosine theta. Okay, so cosine's coming back, yes?
Yes.
So keep in mind, that's the horizontal component. Folks, in an ordered pair, what comes first in an ordered pair when we were just on the unit circle?
Cosine.
It was cosine, right? Okay, it was cosine sine. So the horizontal component is absolute value of v times cosine theta. And the vertical component then, b, is the absolute value of v comma sine theta. So what we talked about earlier as a times I plus b times j, that's what that can be written as. Okay, the idea that a was just defined to be absolute value of v times cosine theta, b was just defined to be absolute value of v times sine theta. That's a way we can find a and b. Okay, sometimes we're given to the head and the tail and we can just subtract them like we did earlier to find component form. Sometimes we don't have that information. And so if we have an angle thrown in, those are the forms we'll look at. Okay? So, and then this one, u is just representing the unit vector here, and this is just saying that a unit vector has a length of 1, so you wouldn't have to worry about the absolute value out front, because the absolute value of the length would be 1. Okay. Let's try and look at A here. I put these on the separator. I should have separated them. Or I guess it's example 4. Find the components of the vector v with a direction angle of 115 degrees and a magnitude of 6. Okay. Break it down. find the components. What are they asking me if they want the components?
The linear
Kind of. What are the pieces we have to know here? We need to know the two pieces, the A and B. Okay, we have to know that horizontal component and that vertical component. So when they say find the components, we're finding A and B of the vector V with a direction angle of 115 degrees. What is that?
theta.
That's theta, yes? It's an angle. That's going to go in for theta. Okay? And a magnitude of 6. What's magnitude of 6 mean?
Absolute value of V.
Yeah, absolute value of V, the length. Okay. Now, we know a theta. We know an absolute value of V. We need to find A and B. How do we find A? According to our formula up above, you do what? A, absolute value of V, times cosine of theta. It's right in the paragraph up above. So what's the absolute value of V?
6.
6 times cosine of 115 degrees. Guess what? That's going to be a calculator problem. Okay? How are we going to find B?
B. 6 times theta.
Okay, B is my vertical component. So we're doing the magnitude or length. So 6 times sine of the direction angle. Yes, it could be a negative.
How many decimals do you go in?
I have 2 decimals on my paper.
-2.54.
Okay, so if you go back to A, and you just flat out plug it into the calculator, of course making sure your calculator's in degrees, you have -2.54. B?
5.44.
I say, I have written down 5.44.
Me too.
Now, I'm going to pause here, and I'm going to say, remind me tomorrow, Monday, that this is where I stopped, and I need to write, well, I guess I could write my answers. There's 2 ways to write the answer. We can write it in component form as A, B, and we could write it in linear combination as A times I plus B times J. Okay, so in component form, -2.54, 5.44. Okay, or we can write it as AI, which is -2.54 times I plus B times J, 5.44 times J.
And those are the answers.
Those are the answers. Now, remind me on Monday, if we think about it, I heard the question, can it be negative? Let me address why the negative makes sense on Monday, okay? Because there's something to connect on. And it just has to do with what quadrant everything's in.